the Chinese or somebody else and applying it practically to factories.
Absolutely
We
true.
want the tickets we never saw.
We are having one of the most important subjects discussed today.
No,
If
the
you
pressure.
don't know it, it's probably one of the most important subjects in this century, and that is energy and nuclear energy. All because we are all involved in AI and all the other things that are working on. But I'd like to introduce our speaker. He was a professor at MIT, but he's still doing a lot of work. Andrew Kadak. I'd like to.
Come up. Okay.
Can you hear it?
Goes in and out.
It goes in and out. Debbie, what can we do?
You can talk to my mic.
Here, you talk. Thank you.
I am your entertainment portion of the program. What I'm going to try to do in the 30 minutes or so is to give you a brief idea of what's going on in the field of nuclear energy.
Can you hear?
I can turn this up or somebody can turn it up. In any case, my background is simple. I started out as a mechanical engineer. I decided that was boring. And in my senior year, I should say, I took a course of introduction to nuclear energy, and that propelled my career to MIT, and I did master's and graduate work at MIT. And one of the projects was the redesign of the MIT reactor, which was a physics project, and it actually needed to work, and it took me about 2 years after that thesis was done, and they redesigned the reactor, that I called up and said, did my thesis work? And thankfully it worked. So I'm greatly relieved. But since that time, I've had a wonderful career in the nuclear field and combustion engineering. And then I was in public relations, believe it or not. This was during the nuclear debate where the Union of Concerned Scientists was complaining about emergency core cooling systems. And some fellow graduate students and I put a paper together called The Nuclear Debate, A Call to Reason, which was a brief pamphlet explaining what nuclear was, what emergency core cooling systems were, and how this is and why this is all important in terms of continued nuclear development. That led me to a public relations career for 4 or 5 years. And everything was going great. We were going to build 2 nuclear power plants in Charlestown. Unfortunately, guess what happened in 1979? 3 Mile Island. They canceled the plants, and since that time, really the nuclear industry has been in quite a down spiral, except recently. So then I came to MIT, and I said, wouldn't that be a fun thing to do for 12 years? And that's where my last engagement was. But I'm going to start with the future of nuclear power. And what I'm going to try to do is give you an outline of basic technologies, what's going on in the world, the current situation we have in the United States, and some future options, of course, and the challenges that nuclear continues to face. This is an amazing time. For those of you who don't know this is your nuclear power plant. Do you know where that is? Port St. Lucie, where I live, within the 10-mile emergency planning zone. And as it were, as a young engineer working for combustion engineering, I worked on the safety analysis of that plant. So I'm happy to report it's run for 40 years, it's almost 50 years old, and it's going to run for another 10, if they don't renew the licenses for another 20. So it's a long-term investment. This is a picture of China, what's going on in China. And although this device does not work, what you see over here are the Diabei nuclear power plants. Those are built in the 1990s. These are 4 new modern Chinese-built reactors. And I was a senior consultant on the safety oversight board for these plants. I've been to China about 5 or 6 times overseeing the safety operation. And I can report to you, they run and build nice, good plants. China now has over 55 nuclear power plants in operation, and they're building 50 more. So they are totally committed to nuclear, and also, as we talked last night, they're also building a lot of coal plants. Now this is the Vogel. These are two new plants. This is AP1000, pressurized water reactors, and these are the two older ones that produces over 4,000 megawatts. That's enough power for 4 million people. And you can see the footprint isn't that large. What most people think about nuclear power, they look at these cooling towers and say, well, that's a nuclear plant. No. The nuclear plant is the little things right here. And the rest of it is all support equipment. We've shut down a lot of nuclear power plants. This is the Palisades Nuclear Power Station, shut down in 2022. And guess what? A company bought the plant for almost nothing. They're intending to tear it down, but this company called Holtec, they said, why don't we try to restart this plant? And this quarter, 2026, they're going to restart that plant. It's the first time ever a shut down nuclear plant has been restarted because they need the power. And Holtec's being clever enough, this is the Palisades plant. They're intending to build 2 of their SMR 300 pressurized water reactors on that same property. That's where things are going these days. Today, the modern thing is small modular reactors. Westinghouse has its version, General Electric has its version. They're smaller only because they're cheaper to build and faster to build. Cheaper in terms of capital required to build it. Instead of like 10 billion or 12 billion, it's maybe 3 billion. So it's an easier asset to finance. Now this is what's going on now really in the marketplace. All these are pictures of advanced small modular reactors. And the important thing is to remember is each one of these is developed by a private investor, a private group of people who are trying to say, I've got a better idea. And there are roughly 88 new developments going on worldwide for this type of technology. This is Oklo. This is a small reactor designed and developed by 2 of my former students. It's a sodium-cooled heat pipe reactor, and they're looking to get into the market for distributed energy, maybe 5 megawatts or so. It's small, but easily deployed. Natrium, this is Bill Gates' project. It's again a sodium-cooled fast reactor with a storage system such that in case they need more power, they can use that heat stored in this part of the reactor to provide more power to the turbines and generators. ALO, this you probably read something about this project. They're very small, 15 megawatt. These reactors are designed to run for 15 years without refueling. NuScale, you've probably read about this. This company has gone public. And what you see here is individual reactors, in this picture 6, in a big, large swimming pool. And if you need to refuel a reactor, you just take one of these, float them around, and put them in the refueling bay, and put a fresh refueled reactor in its place. Each one of these reactors has its own turbine generator. So it's a very flexible design, and they're going to probably build this in Tennessee. Molten salt cooled reactor being developed, got a license to build a demo. And X-Energy, this is my baby. It's a high temperature gas cooled reactor that the Dow Chemical Company is looking to build for their process heat and electricity needs. 94 reactors in the United States. We used to have 104. 18% of our electricity, 43% of the clean energy this country produces. It's not a small figure. 28 states, as you can see. Worldwide, 438 operating reactors, small percent of global generation, but 77 are under construction, as I mentioned, 55 in China. 31 countries use nuclear energy. You can see the number by the countries. Japan used to have 55, but of course the Fukushima accident shut down quite a lot of them. But down here, I don't know if you can see this, these are all the countries that have nuclear power plants, 1 or more reactors. Argentina, Armenia, Belarus, Belgium, Brazil, Bulgaria, Czech Republic, Finland, Hungary, India, South Africa. It just goes on and on. I was amazed by the depth of deployment around the world. Countries interested in building nuclear power plants. Imagine Bangladesh. Why? They need electricity. Egypt and Turkey. Turkey's going to build a Russian plant. Proposed reactors in these countries. All the countries who have provisional plans or indicated an interest in building new nuclear plants. So this is becoming a worldwide phenomenon. I'm going to go over a little bit about the basic technology. I don't know if you're technically aware, but we have two basic types. Light water reactors are pressurized and boiling. We have sodium-cooled fast reactors, these high-energy neutrons. High-temperature helium-cooled reactors, lead-cooled. Russians ran submarines with lead-cooled. Imagine lead being a coolant in a reactor. Molten salt, molten salt fuel, where they dissolve the uranium in the salt, and they circulate it. And the objective is to make steam for conventional power generation. The only thing it does is create heat. So this is how it works. This is a boiling water reactor. The water flows into the reactor core, it converts into steam, goes into a turbine, it's condensed, and then it's recirculated. And this is the body, it goes to either a body of water or a cooling tower like in this picture. A pressurized water reactor, on the other hand, has a reactor vessel, and the water is circulated to a steam generator, where around the steam generator tubes, the water is allowed to boil, going to the turbine and the condenser. So the big difference is there's 3 independent water systems compared to the 2 for a boiling water reactor. Most of the reactors in the world are pressurized water reactors. So everything to the right of this is a conventional fossil plant. So it's no different. The fuel. This is the uranium pellet. It's a ceramic pellet, and it's put into these fuel pins. And these pins are roughly about 12 feet tall, and they're like maybe 250 of these pins in one assembly. A typical reactor would have about 300 or 250 to 300 assemblies in the reactor. And every 2 years or so, they refuel 1/3 of the core and replace it with fresh fuel. So the fuel in the reactor like this spends 3 years in the core before it needs to be refueled. I mentioned pebbles. These are graphite pebbles, graphite balls about the size of a billiard ball, in which 19,000 triso is a silicon carbide coated particle of uranium, is put in, and these balls are recirculated continuously in the pebble bed reactor. So it allows for, you don't need to shut down for refueling, as an example. The capacity additions, you can see in the early 70s and 80s and up to the 90s, we had a lot of new nuclear capacity added. But since 3 Mile Island happened in 1979, these reactors were previously under construction, but nothing's happened until the Vogtle unit number 3 and 4 have come online. So we've been in a big construction shortage of new nuclear power plants because of the cost of these plants largely. And we're now trying to catch up. This is the Vogel's plant. As you can see, a better picture of the old plants and the new plants. This plant, unfortunately, was delayed by 7 years and cost almost 3 times as much as it originally budgeted. Due to bankruptcies, poor management, the plant wasn't completely finished in design, and it was the first of a kind. Everything that's the first of a kind takes a lot longer than you expect. So these plants are being now marketed all around the world, and China has built, in fact, 4 of these before we had our first one operational, which is another story. So we've had, as I mentioned, since 2000, a lot of retirements, 10 shut down. The plants are incredible investments because the original operating license lasts for 40 years. We can extend them by 20, so now we go to 60 years. Most plants who have not been shut down can now operate for 60 years under the current license regime. There have been some plants that have gotten approval to run for 80 years. Imagine that. As old as I am, a nuclear power plant will be around. Maybe they'll go to 100, I don't know. But this is possible with nuclear power. Why is it possible? Because people continue to maintain, replace worn out components, and refurbish the plants. That's the only reason it can happen. And I mentioned others, Palisades, for example. One company called Alba Energy is taking advantage of the existing plants have so much built-in margin. That means additional capacity for producing electricity. One of the plants that we worked on, Vermont Yankee, they increased the power from that single unit 20%. And it's a lot faster to add capacity by upgrading these plants, and Alba Energy is one of the companies proposing to do that for other reactors. And again, it's a long-term investment for the companies invested in nuclear. The drivers that we are looking at right now are obviously the climate change. Data centers are a big thing. Electrification is happening, as you can see. Everything is going on is now being electric. Electric hot water heaters, electric everything. And we're replacing old coal and oil plants. The barriers, it takes a lot of money, $10 billion per plant. That's to build it. That doesn't include all the research and development to get to that point. Time to market, a long time, 10 to 15 years. Right now, if the data centers need a nuclear power plant, they'll have to wait 10 years. They don't have the time to do it. So they're looking for alternatives. And the alternatives uprates for the existing plants, maybe, in fact, restarting some of the other shutdown plants, but they desperately need the power. We've got a lot of political impediments on a state and federal level. Some plants that still ban nuclear development. It's fortunate to see the states of New York and Illinois now embrace nuclear power, where previously they were very vehemently opposed. We've had impactful events. You all know them, 3 Mile Island, Chernobyl, and Fukushima. And the worst of it is, for us, is no political solution to nuclear waste disposal. And if you ask, I can give you a story about that. So, different, as I mentioned, 80 new innovative styles. Microreactors are very small, almost domesticated small plants that run like nuclear batteries. These are under designing, not yet construction. Modular from 5 to 15 to 300, and the large, these are the AP1000 type. The Koreans have a plant that they built in UAE. It was 1,400 megawatts. They built 4 of these reactors in the UAE in record time and put on budget. So the Koreans know how to build. Remember, UAE was a country that had no nuclear experience whatsoever, and they were able to do it quite well with the Koreans. Small modular reactors, why are they so attractive? Because you can build them quickly. They can be factory built, shipped to the site. You can control quality. They're deployed as modules. If you need 50 megawatts, add another 50 next year, 10 years from now. Just add that module. You saw that in NuScale. A lower capital cost initially. And also, they're more easily sited because they're smaller. And they're inherently safe in design. Today, we're using physics and engineering to reduce the risk of nuclear power instead of complicated emergency core cooling systems. This is being driven by new startups. New people have better ideas. Modularity, a quick thing on modularity. You're all familiar with Legos. Apply that concept to a nuclear power plant. We did this one of our designs. There's the reactor, there's all the components necessary to make electricity. You put these components in what you call space frames. So it's like a Lego block, and then you take and modularize the plant. So each one of these space frames could be fit on a truck and shipped to the site. So instead of building it, you assemble it. And that's the concept that some people are actually using. Historically, these are the companies that built reactors. You know the names. Westinghouse, General Electric Combustion Engineering, and Babcock & Wilcox. This company was bought out by Westinghouse. This company is still around. All these startups, and there are more, are privately funded by investors.
All U.S.?
All U.S. I've not included the international ones. The international ones will be another list. But compiling this list and understanding what they're doing was a major research effort for this presentation, which I can't go into. But these are all U.S. companies. You know these people. I think Dale knows every one of these people personally. They've been to her house. They're using now these special purpose acquisition companies. They collect a lot of money, and these companies decide, I'll give it $100 million there, $100 million there, and they finance these startups. And that's the way they go, and some of them are actually going public. Now, you all recognize these companies. Dow Chemical's beating the pebble bed. Google's got a commitments to a number of these small modular reactors. Oracle, Ontario Hydro is building the GE plant in Ontario. Utilities don't want to be first. They're very risk averse. And all they want to do is operate the reactor and not build it because of their Vogtle experience, which is a tragedy. Right now, there's a nuclear scaling initiative underway. Clean Air, these are environmental groups. Clean Air Task Force, Armin Cohen is the head of that. Nuclear Energy Futures, Ernie Moniz, and Nuclear Threat Initiative, a non-proliferation organization. These groups are teaming together to try to create a 10-reactor order book, trying to figure out how to finance, develop, site, construct, and operate, and create this team of people who would be willing to raise $100 billion. And for a lot of people, that's not a lot of money, the previous list of people I showed you who are interested in nuclear. And Jeff Bezos funded, in fact, the study that is leading to this proposal to present to the administration. Again, I can't go over all of these because it's too much information, but these are the high temperature helium, light water reactor, molten salt energy storage, that's the Bill Gates, NuScale, I talked about that, the GE reactor, Westinghouse, molten salt. You can see the varying sizes and the different types of energy levels that these plants are aimed to produce. Every one of these reactors has a market, and that they're trying to capture that market. They will not be built. All of these will not be built. It's just those who will survive will do it very well. Features, mostly modular, quicker to build, safer, designed to prevent core meltdowns. Existing plants depend on emergency core cooling system. These are light water reactors, and new plants are designed to avoid all that stuff, make it easier to build and cheaper to build. Let me give you a quick example of safety. This is a picture of us in a control room in a Chinese small modular reactor, pebble bed, outside of Beijing. Yours truly is standing there. They ran a test using these pebbles I talked about. The plant was operated at full power, and the things that they did to this, they shut down all cooling. In a light water reactor, the reactor will melt in 2 minutes. They prevented the shutdown control rods to shut down the nuclear chain reaction. They restricted any heat removal from this reactor. The light water reactor would go, you'd have TMIs, Chernobyls everywhere. What happened was, because of the physics, the power level of this reactor went down to 0. Why? Because of the physics says, if you heat it up, the reactivity goes down and shuts itself down. The reactors, we left for a tour. About an hour later, we came back, and the reactor cooled down, and it started to heat up, and it went more critical, and then it shut itself down again as it got too hot. That's safety. And even the Union of Concerned Scientists guy, I handed him a pebble at one of the congressional hearings. I said, do you think this is a safe enough reactor? He says he does. Now, Popular Science, not the most technical journal in the world, they featured nuclear power. This is the whole cooling tower. That's the reactor. You can see there's a lot of miscommunication in the public forum about what nuclear is and what is not. Future applications. I'll use this as a Westinghouse example. A nuclear power plant can make hydrogen, electrolysis. It can use or process heat, the excess heat that you don't have to discharge. District heating. Some nuclear power plants in Europe use nuclear energy generated district heat, and they make water, and that's what the UAE is doing. They built nuclear power plants to make water. A lot of money. Financing is tough, as Warren, last name? Delmore, was finding out, and he needs to raise. And, but it's a long-term investment. The nuclear regulatory licensing is very costly, especially if they're not familiar with the technology. Molten salt, liquid sodium, they don't know this stuff. And the staff there needs to get smart on it. But again, it'll take a long time to even build the small ones. The United States government is doing a great job. They're incredibly financing nuclear development. They have this reactor pilot program. They're going to down select the 3 reactors that they can demonstrate in probably at national lab sites. And this is demonstrate by July 2026. That's the goal. A lot of money. He was also involved in the loan program. The Defense Department is very aggressively interested, largely because the Defense Department needs to have reliable, forward-based nuclear reactors. And these are much smaller reactors, but there's a lot going on in the military side of nuclear. The NRC is, under Trump administration, looking at more efficient licensing, risk-informed licensing criteria. I've worked on that for years and years. They're finally getting to that. And this is a thing called other transactional agreements. The DOE, it's a way for the DOE. DOE is going to be the sponsor of these reactors. They will bypass NRC regulation. The DOE will license these pilot demonstrations such that the NRC subsequently can license them for mass deployment. But this brings us back to the old Atomic Energy Commission days, where the AEC used to be able to get stuff online quickly, do technical reviews, and get it done. And national laboratories will be used as a site. Public support. People think everybody hates nuclear power. That's not true. 60%, during the 3 Mile Island days, it went pretty low, I gotta admit. But about 60% of the people support nuclear power, and this is despite all these events. Remember, 3 Mile Island was the only accident that we had in the United States. That was in 1979, a generation or two ago. So even the young people don't even know about 3 Mile Island unless they watch the China Syndrome movie. Of course, they've seen events in Chernobyl and Fukushima, but again, Chernobyl was not a U.S. technology. Fukushima was a natural disaster caused by tidal waves, not necessarily a failure of the nuclear power plant. And of course, we have no solution to nuclear waste yet. Both good news is Democrats and Republicans both support nuclear power, remarkably. We have a senator from Rhode Island, Sheldon Whitehouse, very liberal, big pro-nuclear supporter. Future, breeder reactors. Imagine a reactor that will take like the byproducts of uranium enrichment and makes more fuel than they consume. Infinite supply of fuel right now in storage in barrels at Savannah River and other places around the country. So with a breeder reactor, people are opposed to that because breeder reactors will require recycling and use of plutonium. In a common reactor today, by the end of the useful life of that 3-year cycle, about 30 to 40% of the energy from the uranium fuel comes from plutonium, which it's a natural process. They're looking to use plutonium to in fact, recycle it in light water reactors. But you can use fast neutrons and breed uranium and plutonium and thorium-233 for breeder reactors. Recycling and reprocessing, the French do it, the Russians do it. What this does is reduce the volume of nuclear waste disposed, about 90% reduction in volume. They create a waste form glass. It's like take that piece of glass and say, let's fill it with glass. That's what it turns out to be. And the French have stored and reprocessed a lot of waste, which the residue has been reprocessed and recycled into nuclear power plants. People have talked about floating nuclear power plants. The Russians built a floating nuclear power plant that, in fact, operates a power plant, a town in Siberia, which is, again, a good thing to do. Offshore power plants have been talked about. Super tankers. The Savannah River, the nuclear ship Savannah was commissioned in 1960 and ran for about 10 years, nuclear-powered container ship, and at that time they didn't have container ships, but it was a commercial shipping line that also took passengers. The problem with nuclear-powered supertankers is some ports will not allow a nuclear ship into their facilities, and that'll be overcome. Home heating and cooling. There's patents out there that will allow for nuclear waste to be encapsulated in a glass form and given to you like an oil truck comes, and you give a little capsule of that and provide heat and power for your entire house. And we did a project that goes to Mars. The only way we're going to man, or at least do anything serious in outer planets is with nuclear energy, because solar is just not effective at that distance. The future depends on continued government support. Obviously, these demonstrations have to be quite successful. Private investment must continue. The AI centers need to be built. And this is very important. Right now, because we haven't built anything for so many years, the infrastructure, the manufacturing capability doesn't exist. The trained workforce doesn't exist. The plan is to build 300,000 megawatt reactors by 2050. It's going to be really hard to do if we're going to meet our energy demands at that time. Message. A lot of innovation, a lot of worldwide interest, incredible. I think the nuclear looks bright. I think private investment continues to pour into nuclear. The data centers are willing to pay much more for the reliability than the utilities are. And that price, because they're willing to pay that price, they're willing to invest in these new developments. We will need a lot of big plants, as I mentioned earlier, but small modular reactors will be, I think, the dominant force in the future because of their flexibility and cost. So with that, I'm willing to answer any and all of your questions. Oh, my goodness sake. Start with this. Oh, you need a mic. Just one moment. We got it. How about right here? Can we do this? There you go.
Fusion.
Yes. What's the question?
The Chinese seem to have made considerable progress on it.
Yes.
Is it the future? Does it replace all of this? Is it infinite supply of energy? What's the story on fusion?
I am so glad you asked, because what about fusion? Okay, there's a lot of international work going on. There are 44 test facilities around the world, as you mentioned, China, Japan, Russia, and the US. I just featured a couple of these companies, and this technology won't make any sense to you, but this is the only one that I was able to find that can make direct electricity from the fusion reaction to direct the electricity. TAEI is another particle accelerator. That means instead of using high energy like microwaves, they use an accelerator to create this high temperature needed. Inertial confinement, Lawrence Livermore is developing that, and Commonwealth Fusion Systems, they're from Massachusetts. Their big contribution is advanced magnets. Well, here's the problem. You got to get more energy out than you put in. To make a plasma takes a lot of energy, as I'll show you in a second. It's the engineering of it that's going to be the limitation, not the physics. They know how to fuse stuff. The question is why, when alternatives exist and available. The promise of fusion is inexhaustible fuel supply. Free. It's only water. Not true. But it's deuterium and tritium. Let me go back. Here's what you got to do. You got to create the condition of the sun, 100 million to 200. The sun is only 15 million degrees centigrade. You got to do that by combining two atoms, which as a gas, combining them long enough so that they have enough energy to overcome the Coulomb barrier, which naturally keeps them from trying to combine. And you need to do that at these temperatures, 916, well, the magnets have to be kept at 9, but the temperatures that they need to create is 100 million. The magnets, to do that, they have to be superconducting to be able to confine this plasma, and that's a low temperature. You got to do this continuously. That's called a burning plasma. And what are you going to do? You're going to boil water. I think that's kind of not such a good idea. There are other ways to boil water. Many of these technologies, that's all they want to do. Some, as I pointed out, the direct helium, electricity conversion, that's good. But again, as I mentioned, it's a physics challenge, not an engineering challenge. Let me go back to here. So, I think I have a picture of this. Sorry. There. This is a tokamak. They operated one of these at MIT, very high magnetic field, so they create the plasma in this zone, and then after putting enough heat and energy into this plasma, it's like an ionized gas. It sparks, and that's success. But the energy it takes to make this plasma is enormous. This is the National Ignition Test Facility. 192 lasers focused on a little capsule of gold that contains deuterium and helium, deuterium and tritium gas. All these lasers are designed to blow up this gold such that it collapses and creates this incredible force to allow the deuterium and tritium to fuse. One spark. When I was there, they were able to do 2 shots a day. For this to be successful commercially, they need 10 shots a second. And this facility is massive. Imagine the amount of energy it takes to power 192 lasers.
Do you think it's the future or not?
I don't think it's going to work commercially, not in my lifetime. This is the ITER in France being built. It's the largest tokamak ever. And they're not going to make electricity. They're just going to prove the concept of large confinement with more energy out than you put in. This is their pulse plasma machine, and this is the particle injection build of TAE with reverse confinement. So when I was in school in the 70s, 35 years from now, you'll see fusion. They're saying 25 years now, you'll see fusion. Technically doable, do you need to do it, especially when you have alternatives?
Are the Chinese doing it?
Chinese are doing the same thing that we're trying to do here. Yes, ma'am. Well, who's got the mic?
Hello.
I'm sorry.
19th century steam engines were very inefficient in,
Very inefficient.
Transmitting energy from the fuel into useful work. The nuclear power plants are using steam. How efficient are they in transferring energy? And is there a conceivable future where something, if they're not efficient, might be more efficient?
Okay. A typical light water reactor is about 33% efficient. That means 2/3 of the heat is rejected into the environment, either in the water or in the air. The reason why these alternative applications are valuable is because they can use that unused energy in desalinization, in district heating, perhaps hydrogen production. We're not at that point yet because there's still an aversion to using nuclear because they're afraid of contamination. So if you're tied into a nuclear system, you have the potential for contaminating your district heating supply. I think we're going to overcome that shortly. The higher the temperature of the reactor, that's why they're going to molten salts where it's 700 degrees centigrade. And that 700 degrees centigrade efficiency could be upwards of 40 to 50%. That's about as good as, that's a Rankine cycle limitation. Yes, ma'am. Well,
I have a question here.
who's that? Okay. I'm trying to find the mic.
I wanted to know how many reactors we have in America. I would assume a fair number are old. And is there any companies thinking about restoration of old to make it new again?
Well, as I mentioned, there are 94 reactors, and during the operating life of these reactors, they're refurbished essentially continuously. And that's why they're able to run under Nuclear Regulatory Commission license for 60 and then some for 80 years.
And what about after 80 years?
We don't know. We don't know.
Must be a way in the future for that to
Imagine, I don't know if any power plant of any type is operated for more than 80 years.
I have a question, please.
I hear you. Oh, yeah.
Actually, two questions. How do you compare the costs? We talked about efficiency, but how do you compare cost of running a nuclear reactor to running a traditional power plant?
You mean a coal plant?
How much water do they use? When we hear all this work about how much electricity AI is going to use, how does that help us? And then my last question is totally different, and that is, right now there are talks going on with Iran about the whole nuclear question. And Iran says, yes, we can build a nuclear plant, but it won't develop into a bomb. But how true is that, or
Okay.
is there a
Let me
bomb?
start with the last question because that's the one I remember. Sorry. The Iranian situation, they claim that their interest in atomic energy is peaceful. But I can tell you, you do not need 60% enrichment to make a nuclear power plant. You need 5%. So why they enrich the 60 is only for one purpose, to use that to make a nuclear weapon, period. No other comments.
Why doesn't that come out in other words, why doesn't that come out on the press and hit the people hard that they're full of baloney when they're saying?
I can't address that. Perhaps our guest over here might explain why that doesn't happen from the New York Times of all papers. Okay. So I think the only way it's going to work out is if Iran allows full inspection of all their nuclear facilities. Whether they do it or not, that's the open-ended question. Now, your other question was?
About the efficiency of a nuclear plant versus
fossil.
traditional, and the cost effectiveness, return on investment.
Okay.
When you talk about they're spending billions of dollars to build it, how effective is it?
Well, the efficient use of capital, is that the question? The way it works is, in a regulated utility, you are reimbursed for your cost of capital, and they're allowed a certain rate of return. And they have to, of course, sell power at competitive rates, otherwise they can't compete with their utility partners. So that's why nuclear is such an obstacle in terms of getting it built. And that's what people are looking for, the smaller reactors that will not be as capital intensive. Most utilities can't put $10 billion on the balance sheet. They're not big enough. Bill Gates could. The data centers can. It's chump change for these people. And that's why the data centers are driving the push towards nuclear. Now, another question.
Yes, hi. I've always wondered, and I'm old enough to have watched the history of some of the nuclear failures in Fukushima, which were still undergoing problems from dumping in the ocean isn't a solution. When there is, as you said, no solution for the waste, which is harmful, toxic, how wise is it to keep producing something we don't have a solution for?
Next question. An excellent question. And not that I'm a soothsayer, but I was kind of thinking that would come up. Let me see if I can get the slide. What about the waste? Let me give a little history. In 1987, the Nuclear Waste Policy Act designated Yucca Mountain as the final geological repository. The United States spent $15 billion researching that mountain. What you see here is a picture of one of the tunnels they built to study the mountain where the waste would finally be in place, geologically disposed of for millions, hundreds of thousands of years. This is Yucca Mountain on the border of the Nevada test site. Congress decided that's where they wanted to put it. This is probably the first time that Congress actually used their brain. Why not put it where we used to test nuclear weapons or nearby? It's already contaminated land, so we're not going to make it any less contaminated, any more contaminated, I should say. So they spent all this money. In 2008, the Nuclear Regulatory Commission issued a preliminary safety evaluation summarizing all the studies. And they submitted it to the the Department of Energy submitted this to the Nuclear Regulatory Commission for review. The NRC reviewed the document and was prepared to issue a draft safety evaluation report in 2010 to begin public hearings on this issue. Guess what happened? Politics got involved. And President Obama said, I owe it to Senator Reid of Nevada to stop this project because he doesn't want it in this state. Even though Congress, in their passing of this law, allowed the states to veto the plant subject to congressional override, which was overridden. So we're now at a point where there's no plan to restart Yucca Mountain. There's no plan to even site such a facility. And the answer to your question is, why do we continue to operate nuclear power plants? Because there is no political solution is a good question. Because Congress knows about this. This is the law of the land. Congress can ignore the law of the land. That's okay, apparently. So we're now in a situation where we used to be ahead. Finland and Sweden are now building their own repository, a geological repository. It's at the site of one of their existing nuclear power plants. Each one of them has different nuclear power plants. And they're building it at their sites. So it's a doable, not technically impossible situation. And the reason why we continue to build it is because we have to wait for the politicians to decide to let's go do this as a responsible thing that our government needs to do. Hello? So where is the waste? Okay? This is, I mentioned earlier, this is the site of the Yankee Atomic Nuclear Power Plant. It used to be here. What you see in the background is these kinds of canisters, concrete shielded containers, which contain all that spent fuel, those assemblies that I talked to you about. They're in these canisters, waiting for the Department of Energy to come and pick them up.
Which are only good for how long before they disintegrate?
They don't disintegrate. These are concrete. They're designed for 100 years. Ask Ernie Moniz. He will tell you. He'd rather see a 250-year storage cycle than a disposal site at this point. Because his primary concern is reprocessing. But that's another story.
And how much do these smaller plants create waste?
By volume, it's the same. Because each, it's a small, low enrichment. They produce, it's a nuclear process. Some of these reactors produce slightly more volume, but you can disperse them in Yucca Mountain in much closer arrays. But this is where they are. At all of your nuclear power plant sites and around the country, that's where the waste is sitting. And the tragedy is there's no nuclear plant there anymore. And the government is not allowed to build an interim storage facility because the law says you can't. But the law also says you need to put it in Yucca Mountain until it's changed. So we're in a catch-22, but don't blame the industry for not having a solution, because we had one. Yes, ma'am.
Do you think they
I'm sorry, got the mic over there.
One, when a plant is deactivated.
Yes.
And mothballed, how safe is it? And secondly, what is the cost to deactivate and mothball plant so it's safe? Second question, with regard to China, that they're building 50 nuclear plants, is there any military use to the waste that they produce at those plants?
Yes. The answer is, yeah. I'll do the last question first, that's the one I remember.
The cost of mothballing and how safe it is to mothball plants.
I have a special lecture for that. I lecture at MIT about decommissioning. But the cost roughly is about $1 billion for a large commercial reactor. It's almost as much as it costs to build, which is in today's dollars. Okay, so it's expensive, but it's doable. There are a number of nuclear power plants, not only Roe, have been decommissioned. Zion in Illinois has been decommissioned. Big Rock Point, gone. A number of others, but I can't remember all of them. But it's a lot of money. But the goal is, go on back. I lost you. The goal is to restore the site to its previous condition. Greenfield, that's what it's called. Some plants are kept in mothballs, which means they're safe store. They maintain the plant waiting for ultimate decommissioning. Maybe they don't have money in the decommissioning trust fund. I should mention, the monies for decommissioning come from the ratepayers that use the power. They have a separate trust of money, upwards of $1 billion, that would allow that plant to be decommissioned. So there's no more additional cost to the consumers because you're already paying that in the cost of electricity from a nuclear power station. So that was the answer to the first question. What was the second question?
The second question was, with China building 50 plants.
Oh, yes.
Is there
Okay.
a waste for military use?
In reprocessing, what you do is you separate the uranium that's still left, unburned, unused, and plutonium, plutonium-239. The plutonium-239 can be mixed with the uranium to make mixed oxide fuel to put it back in the reactor, further efficiently using it. They can, if they wish, take that plutonium and use it to make a nuclear weapon.
Yes. Question.
I'm hearing people.
Thank you very much for your presentation.
But I don't, oh, well, there you are. I'm sorry. I hear the voice.
Two questions. One, what is the cost of this versus non-nuclear alternatives, solar versus wind, et cetera, and are those viable alternatives? And two, given the fact that China was the country that gave us the Wuhan virus and that I wouldn't trust them to build anything because they don't care what happens to their own people. You say that this is a political problem, nuclear power, but if 40% of the country, 60% approves, 40% do not, and a lot of those people happen to be in Nevada during an election, how do you really get around this political problem when I think a lot of the problem for nuclear remains trust in the government and what we're being told?
That's a very good point. Now, the trust factor is based on, I think, knowledge and experience. If you go to every nuclear power plant site in the country, you will see a community that embraces the technology. They're not afraid of it because they trust the people who run the plant. And this is true with the Yankee Row plant. Every plant that I know of, there's a strong community support for that plant. It's for people who don't know about the technology. You said Nevada doesn't have a single nuclear power plant, okay? And they've been told, I think unfairly, the consequences of what happens at Yucca Mountain. I served on the U.S. Nuclear Waste Technology Review Board for 8 years, presidential appointee, to oversee the DOE's research and development program. And I can honestly say the technology that they've developed would safely assure that that stuff can be stored for tens of thousands of years, without ever coming back into the environment. They've done numerous simulations, numerous studies, and obviously that message does not get out. I taught a course in nuclear waste disposal, and I had the students recalculate the models that the DOE scientists and engineers use to predict when and if anything would happen to these waste canisters. And they too were impressed by the degree of protection that's provided. The only way these canisters can become a mobile problem is if water gets into the thing. To address that question, they built shields like umbrellas over these waste packages. And these waste packages are built of these metal alloys that are resistive to corrosion. And then if you get past that waste package, then you have the fuel itself that is itself very corrosive resistant. So you got all these different barriers, but try to explain that to the public who has an attention span not very long. And not that they're uninterested, but they're easily frightened.
Seismic tremors?
Seismic is addressed. You know, it's part of the modeling. Seismic, when we first started, the requirement was 10,000 years. The pyramids were, what, 5,000? And this is a society that was able to build something that lasts on the surface for 4,000 years without a lot of high technology. They protected the monarchs. Somehow, I think we can do better today. Buried like half a mile or 2 miles down in the rock.
Solar versus wind?
Solar versus wind. The only difficulty with solar is it's not available 24/7. Most people want 24/7 power, especially the data centers. Wind, same argument. You know, look at today. Well, you got a little bit of a breeze. But when I came here this morning, there was no wind. So we shut down everything because we got no power? No. I would say it's not a steady, reliable source of power. And it's what we're talking for nuclear base load power. California right now, during the day, gets 90% of its electricity from solar and wind. Amazing number. I said, good for them. But when it gets dark, that number goes down to 0. And then what do? You have the nuclear backup. Right now, I work on a nuclear safety oversight committee for Diablo Canyon. And at Diablo Canyon, one plant supplies 10% of the power of the state. 10%. And even Governor Newsom decided that we need to keep this plant operational because of the reliability and grid stability. So nuclear is, again, you can compete with solar and wind, but you can't compete with the reliability.
Does wind work?
Who's got the mic?
I do. So since this is a two-question lunch.
Few question, I'm ready.
My first question was, just to be clear, none of the data centers are currently using nuclear power to cool them or create
They may be tied into the grid, but if they're operational, they may be tied into the grid, which is picking off whatever nuclear generation is on that mix.
So why are these big companies on the NASDAQ, why are they not, being more forceful in investing in this?
Data investing in data centers?
Data centers, cooling, it's all here about cooling data centers.
The cooling, electricity is needed for the cooling, right? And the companies that I listed before are investing in developing these new technologies in the hopes that once they're fully developed, they can use them to power their data centers.
It's going to be a long way off.
I would say in the next 5 years, we should have some of these plants demonstrated and available for commercial application.
Okay, my second question is just, what do you think about the viability of Mars being the dumping place for all of this?
No.
And do you think Elon Musk, it's his intention?
No. Mars, people were talking about, why don't we send all this waste up to space? That's that's not even on the table. I'm sorry. First of all, to launch something in space, uranium is heavy. It's lead, eventually. And to launch something up in space is very expensive by pound. So to launch like pieces of rock up in space doesn't make any sense to me.
Just to, if I could
I hear you.
follow up to Miller's question, to what extent, if any, do you think that the solar industry and the wind industry and maybe enemies of the United States are actually funding the anti-nuclear movements, environmentalists and others who've been working for decades to undermine the credibility of the nuclear industry?
I don't have any evidence of that, but the anti-nuclear groups are in fact very well funded. And I'll tell you a personal story. When I was in the public information office at New England Power in Charleston, we're hopefully building 2 large pressurized water reactors, like Seabrook vintage. A wealthy person from Watch Hill, maybe some of you live there, invited me to come to listen to a presentation by a guy by the name of Myron Cherry. He was a lawyer, you know. He was a lawyer who was seeking money from very wealthy people, many of them who are here. And he was, the person just invited me to just sit down and listen to what he was saying. Well, I sat there, didn't say a word, and all of a sudden, somebody asked me, what do you think about what he just said? And I said, well, unfortunately, it's not true. then I began to explain what the truth was about how nuclear reactors work and what are the safety systems that are in that. He got not a penny from that group. Okay? There are a lot of very well-being, wealthy people who want to protect us. Need to be better informed before they spend their money doing things like that. I don't care what it is. Generally, get outside opinions before you donate.
Yes.
Yes, ma'am. Somebody's got the mic. Who's got the mic? Oh, you? Okay, I'm sorry.
A two-part question. Number one, if you could do the PR differently or better, what would three thrusts be for you to get people to be more positively informed about this wonderful?
One of my original challenges when I left the technical world to go into the public relations world was I wanted to see if a scientist, allegedly me, can communicate technical information. Very hard. Extremely hard. Because there's so much already ingrained in people's opinions that it's hard to change their minds. That they have this, you know, the anti-nuclear movement started with the anti-war movement. The bombs, the nuclear bomb, they translated that into anti-nuclear power from anti-nuclear weapons. I was never in the weapons field, so I don't know that part of the business, so-called. But they used that bomb fear to translate that into nuclear fear. And we just, the industry hasn't really done much. The St. Lucie nuclear power plant used to have a sign that said, St. Lucie nuclear power plant. Now it doesn't say that. It says St. Nuclear power plant. St. Lucie power plant, not St. Nuclear. So I'm saying to myself, okay, they succumbed. They used to have a beautiful information center. I took one of my nieces, we drove up to the containment. I mean, literally between me and that wall is the reactor containment, that big concrete thing. That's what you need. You need to expose people to what it really is to show them what it is not. And I think that's the thing. And obviously, you need to work with your media. The media they're the eyes and ears of the public. And unfortunately today, we've kind of lost that objectivity.
It sounds like you need more specialists in PR and marketing to really get this.
It's not so much marketing, really. It's just
PR, public relations.
Yeah.
Really understand that, what you're explaining. But I have a second part to my question. So, aside from the PR issue, this is such an ambitious program that you're outlining. Do we have up-and-coming engineers, students? Do we have the people who are going to be behind these new installations? How are we training enough people? Are we getting enough people? Do we have to import them?
That is such an excellent question. Right now, these people that I showed you on that chart, the upstarts, private, they're all young people. They're innovative, clear thinkers. I want to do good. And that's who is now being attracted to the nuclear field. And I'm very encouraged by that. And the MIT undergraduate program, believe it or not, for a school like that, we only had about 30 undergraduates in the nuclear engineering department. That's very small. But MIT decided, even though it's small, they're going to keep it because of its importance. We have a reactor on Cambridge, in Cambridge. Cambridge is a nuclear-free zone. Duh. There was a referendum in Cambridge, again, a duh question. They wanted to not shut down the reactor, but move it somewhere else. I mean, a little bit on the not so smart side. But that's what we're dealing with, unfortunately. And you start with high school. You start with college. The Atomic Energy Commission used to have a program called This Atomic World. And they introduced nuclear to young people so that they were not afraid of it. And they explained what fission was, explained how reactors work, how atomic energy is used, or atomic medicine. All these things are like in medical applications. That they don't do that anymore for fear of promoting nuclear. God forbid the government promotes something like good. So I'm sorry, go ahead.
Well, one of my mentors years ago was one of the heads of Port Authority in New York. And he was a Harvard graduate. And we used to have a lot of talks about diversification in energy.
Yes.
Because, and it seems in the media and in the talking heads world, I'm anti-wind, I'm anti-oil, I'm anti-gas, I'm anti-nuclear. So there's a whole culture that's anti that, and we always say you throw the baby out with the bathwater.
Right.
So and I have one of my grandsons now, is our first engineer genius in the family.
Good for him.
He works with 3M, and he was a biomechanical major. He couldn't figure out what he's doing. But we're very much into the sciences, have been. And what, I hesitate to mention his name, but it's John Lister. And he's related to the Bach family in Harvard. And I loved him, and he was an amazing thinker as far as I'm concerned. So we're into education across the boards. We did a lot of music together. But that's what we need. And my grandson is 30. They had it. So what we need to do is, according to what John used to propose, is embrace diversification instead of being anti-natural gas, anti-oil, the resources, and we're seeing it politically in spades around the world now. It's always the competition for oil. It's coal. We had the anti-coal movement here in our country, and now we're resurrecting clean coal.
Right.
So that's my point, is keep allowing people to be those adventure people, exploring nature. Have the students. I have loved going to I was thinking when you were doing this.
What's your question?
Oh, my question, well, I'm sorry. I guess I'm making a wrap-up question. I'm sorry about that. Excuse me if I digressed a little bit. But basically, I'm making the case for, and I can ask you now specifically, what do you feel about diversification and the use, a little wind here, a little solar there, a little nuclear here, diversification and use of?
Where diversification is excellent, where it makes sense, okay? A lot of people are opposed to windmills off Nantucket. You've heard about that big debate. And in Cape Cod Bay. And my only issue is, what other alternatives are there that would justify that? I don't mind necessarily windmills at all, wind machines, but they come at a price too. And I'm not going to say it's not negative, but we have to establish, I told you, a decommissioning trust funds for nuclear power plants to be decommissioned and removed from the planet. On the wind machines, these companies are in it for a 7-year turnaround. If the machines stop operating, they just leave them there. There's no plan to get rid of them once they stop their useful life. They do work. My favorite windmills counting expedition is I go to Block Island regularly, and I count the number of windmills that are not functioning. Normally it's 1 out of 5 that are not working. And it costs a lot of money to repair those things. They're way up high, 250 feet up off the surface of the earth. But with your thought, I agree with it. Be diversified. And I'm not saying nuclear is necessary to be 100%. Not a good idea. Solar is a good idea. Like I mentioned, California, 90%. But they're paying a price. Wind, look at Europe. Look at the energy costs in Europe. They're double our energy costs. We are blessed here in Florida. Blessed. My electricity rate is 2 to 3 times lower here than in Massachusetts. Why? Because they didn't diversify. They prohibited gas pipelines to New England. Bingo.
This is our last question.
I have one more question. I'm afraid it might take time.
Okay.
I just went to a lecture about China having nuclear reactors in space. You showed us what nuclear reactors are. How can that happen?
I don't know. The only reason to put a nuclear reactor in space is because you need a large power source in space. Now, why would you need a large power source in the middle of nothing? Don't know. It could be a weapon.
That's what it was about.
Yeah, well, there you go.
Security.
It could be a weapon. But they're easily taken care of because they need them necessarily big and they're easily spotted. So I'm not too worried about nuclear reactors in space at this point. All right, thank you.